박정규 박사, 안녕하세요.
네, 안녕하세요.
반갑습니다. 네, 시간이 돼서 우리 시작할게요. Uh, Now let's get started. Welcome to Data Science Seminar. Today we have a very distinguished speaker, Dr. Jongdu Park from Meta. He's working on AI systems co-design. And he did undergraduate at SNU, our university, in electrical engineering, and then I think went to University of Michigan for computer science, and he did a PhD there, and then he worked for Google, I think at TPU, and then joined the Meta. Now I look forward to hearing, this new latest the cases of Meta. Go ahead, Dr. Park.
Yeah, thank you for the invite and introduction. My name is Jason. I'm a software engineer at Meta. Today I'll be talking about AI systems co-design, focusing on the case studies. I put the title as case studies because I'm sort of going through all the experiences I had and trying to derive takeaways rather than being sort of academically rigorous on deriving those kind of takeaways. Before going into details, I wanted to introduce a little bit about myself. So as Professor Cha mentioned, I worked at Google for 5 years. I worked on Edge TPU. The first generation went into Coral AI boards. It's USB stick and PCB boards that you can buy and run stuff with TensorFlow Lite. And then next generations went into Pixel as part of Tensor SoC. And part of it is basically HTPU that runs a lot of vision-related models on Pixel phones. 2-3 years ago, I moved to Meta. When I first started, I worked on recommendation models. And then right now I work on Llama, but mostly focus on the inference side of stuff. So I want to start with what is AI systems co-design. At high level, it's really about machine learning model and the system it runs on, including hardware and then software. This seems a little bit simple, but I'll give you some ideas
오늘은
on.
큰일 날 뻔했다. 근데 사실 이 방에 이미 약간 느낌 늦었거든.
Okay, I'll proceed. So some examples of this co-design is somewhat simple, but I'll go in each pair. So easiest one is basically how hardware sort of influenced the model design. And probably many of you already know, but if you look at how tensor shapes like weights or even activations or intermediate tensors, your innermost dimension is usually a multiple of 32. And this is mainly because NVIDIA's GPU warp size is 32, and being multiple of 32 basically gives you best performance without if you are not being multiple of 32. Similarly, like you probably have heard about like TPU, HTPU was one of the things I worked on. MTIA is something my team also works on. Amazon has Trainium and Inferentia. Microsoft has Maya. And then there are a bunch of startups here in Korea as well as US. There's a bunch of them. But basically, the idea is for ML models, they can design a custom accelerator which can accelerate them better than say CPUs or GPUs or existing architectures. Similarly, model also influences software frameworks. You probably already know about PyTorch and TensorFlow are probably top 2 frameworks that people use these days. And things like AutoGrad from PyTorch sort of gives you a way to sort of design a model, and then you just run it without worrying about how do you backpropagate certain ops, or how do you design an op to run efficiently on GPUs without worrying all those kind of stuff. You can simply run ML model, although it might not be the best performance, but you can sort of run things out of the box without worrying too much. Similarly, because you have such software frameworks, you would see that a lot of model architectures transfers quickly to other tasks. One example before all this transformer thing was that convolution was very successful for vision models. And you'd see convolution being used for like natural language models, even audios or wherever they can apply. Even though like conceptually convolution doesn't seem to make sense, it did generalize well and did well on those tasks. And same for attention and transformer. It started from translation or NLP side of tasks. But now, if you look at recommendations or even vision models, you'll see that transformer may not be used as exactly the same form as NLP, but at least attention is used quite often in most of the new type of models. Hardware influencing software is mostly from the CUDA or front-end languages. So CUDA has been there for almost 20 years now. And this is one of the, like people say this is one of the reasons why NVIDIA GPU is so successful. And it's hard for others to catch up, like AMD or other parts. But you'll see that Triton from OpenAI is a also recent thing, where they initially it was targeting NVIDIA GPUs only, but a lot of people are trying to use Triton as a front language for their accelerator because people are writing in Triton, and if you have backend ready, then you can port those kind of stuff without worrying too much. And this would be much easier than trying to port CUDA corners. Like if you look at AMD, they try to use hipification to sort of port CUDA stuff to their ends, but like it takes a lot of effort compared to say Triton corners. And also there's if you look at compiler domain, there's MLIR. This is part of LLVM infrastructure. This has been a huge success. And I've seen a lot of companies working on accelerators adopt MLIR as part of their backend compiler, mainly because it gives a lot of good toolings, good ways to look at how it works, and it also provides a lot of basic functionalities like code motions or whatever, that code elimination. Those kind of stuff is sort of already available in MLIR. And then there's concept of dialects, which you can use to sort of like extend and make it work for your accelerator without too much problem. On the other side, like one thing we have realized when we're doing software side is that, I mean, we have seen that in even on CPU land, we started seeing sort of saturation in single core performance, and we started doing parallelisms, concurrencies across multiple cores. And this is also becoming an issue on the machine learning side as well. And in a lot of cases, we try to use concurrency to improve hardware utilization. And it like stream events are common things that was introduced by NVIDIA GPUs. And if you look at PyTorch, like a lot of like AMD or other accelerators, they would adopt a similar concept and just implement it and support it. Because even if you today think there's a better way to support it, like a lot of people are already using streams and events, and it's hard to move the ecosystem towards the other side of the way you want to move. And obviously, another thing is you want to have non-blocking transfers between hardware and like the accelerator and CPU, because that way you don't have to block GPU or CPU from doing stuff. So I did briefly give some examples, but if you look at the whole space is much larger. Like model, like their CNNs, recommendations, LLMs. Hardware side, we talked about accelerators, but you have to consider about the memory, HBMs, network. Software side, you have to think about frameworks, kernel, compiler, like runtime, and then there's something we don't really say much is dev efficiency. Is how do you make sure researchers sort of develop models faster and faster without worrying about all the implications. So why do we think this is an important area to invest on? So one thing is it has very diverse requirements. This is a slide I took from one of the talks from Meta. If you look at it, this is showing recommendation versus large language models and showing 7 different aspects like network, scale, model size, memory, compute, how things are being required for each cases. And if you look at recommendations, there's a difference between training and inference, how they require stuff. And then if you look at large language models, there's training inference gap, but there's also prefill and decode differences because prefill is more compute bound, decode is usually memory bound. So as we have seen, there's various different requirements across different applications. And one of the trends we are seeing in training especially is that machine learning models tend to increase compute data model size a lot because as you scale them together, you usually get better quality. And if you want to do that because you are like data and model size sort of maps to memory, and then compute means raw compute, you have to scale the system, the training system to match it. So here I'm showing cloud TPU scaling numbers across 10 years from the past. And you'll see that the y-axis is left on is the compute, right is the memory capacity. And this is for a single pod, which is basically a group of TPUs that are connected through the optical network to provide high bandwidth. And I mean, there's a lot of jumps since 2022, 23-ish, where the large language models start to come in. But even before that, you will see that it's sort of increasing in a very fast manner. And this is being achieved by not just improving the accelerator itself, but it's also increasing the size in the pod. So for example, if I remember correctly, like initial pod size was around like 1,000-ish. Right now, I believe it can go up to 8K, for example. Similarly, if you look at inference, especially on the large language models, this is what I just collected from the websites. So AWS, if you are trying to take some CPU instance and run it, a typical cost is from 0.003 per hour to 20 cents-ish. But if you want to rent 800, just single GPU, it could go from like $4 per hour to $6.6 per hour. So like just using the single 800 versus CPU, you are going to pay 22,000x more cost. Even worse, what is the problem is that the typical QPS is very different and it's actually worse for LM inference. If you look at CPU side, I mean, it's very diverse across what you're using, like versus DB versus like, I don't know, typical like search algorithms or MapReduce type of workload. It can vary a lot in terms of QPS, but compared to that, if you look at how we are running stuff for GenAI LLM inference, it's much lower, like it's less than single digit. I took the numbers from artificial analysis and VLM. And even here, like VLM high-end side is when we are not worried about the latency constraints. So in a case where you're online serving people and you have tight latency requirements, even 4 is probably not something you can achieve. So here you will be seeing another 10 to 1,000x gaps, which means if you calculate the serving cost, assuming like 10K QPS is requirement, the gap is like, I don't know, at least few hundreds to a few tens of thousands difference between the costs. And what this means is if you think of like business terms, right? Like if you are building some application that runs on CPUs and build something and scale and then extract some business values. It's pretty simple because you're spending dollar per hour, and as long as you have sufficient user base and sufficient thing you can get the revenue from, you can probably have a very lucrative business. But for LM, if you are thinking of actually using this to come up with a good business case, it's going to be much harder because the operating cost is much larger. And people, you might have already seen that OpenAI is still losing money a lot these days. And that's there's training cost, of course, but it's also inference cost is not as cheap as traditional applications. And then another part is the environment is also different. So like LLMs, much of stuff we can run it on data centers, but in some cases you might run on edge devices. So some differences are like batching data center, you have to do it and you have enough QPS to batch stuff. But edge, usually you interact with one or a couple users, so you cannot do batching a lot. Also, edge is resource constrained. Your form factor limits your area. You're limited by battery, so power as well. Versus data center, like these days, you can do liquid cooling, which means your power budget is almost like not unlimited, but much higher than what you could have imagined. And the most reason people go for edge is because in terms of privacy, like data centers, you have to shift stuff to data center versus edge. It doesn't have to leave the device. So people are advocating for edge cases because of data sharing or privacy reasons. And companies also have reasons to push for edge device, because if you think of it, data center is sort of centralized cost and you have to pay for it and you have to make up for it in a different way. But if you're selling, say, phones and you're putting TPUs in there, you can add that cost to the users. So for example, if you are able to run large language models on device, then I could imagine like people would just deploy it on the phone and not use data centers for deployments. So to recap, like cost is very high for this AI systems these days. And then as I said, in ML trends, compute data model size continues to grow. So in this case, in this scenario, we'll still keep continuing to see that you have to co-design model hardware software, because otherwise you cannot manage the cost or infrastructure. So now we'll sort of somewhat switch gears and go into somewhat technical stuff. So I'll start with the large language model inference because that's what I've been focusing on these days. And then I'll go for some of the takeaways I've seen, but there I'll be sort of merging stuff from what I learned from HTPU as well. So it's not going to be very consistent on the contents, but bear with me because this is case study, so I had to sort of do that. So large language models, probably most people know, is taking decode-only portion from original transformer paper. It has two parts, attention and FFN. Both of them can be sparse or dense. Sparse attention is something still a lot of hot topic on research across like local attention, Yoko, or whatever type of attentions. And there's no single thing that I think industry has sort of converged onto yet. But for FFN, like sparse FFN is mostly implemented as part of a mixture of experts. There are some variations. For example, on Llama, they used a shared expert, but the original MOE paper or proposal didn't have shared expert. And like there are minor differences here and there, but this is sort of where things are at. When you're running the inference, things are autoregressive. So which means you generate some output and then you use that output as an input for next step and you generate next one. And in inference, although compute or ops are the same between prefill and decode, They show very diverse characteristics, as we discussed in the motivational slides. Like prefill processes n input tokens and outputs one token. And because you are processing n inputs, that means you are likely compute bound. Versus decode, you are basically computing for one token, and your past sort of attention comes from KV cache, which means it's likely become more memory bound. So this is what I took for a recent NVIDIA Dynamo related article, but you'll see that QKV, because of QKV computation, prefill is more compute bound, and then on decode side, we can use KV cache, which means that it becomes more memory bound. And you can do batching and other stuff to mitigate the problem for decode, but it's still limited. So one idea that has been around for a while is disaggregated serving. So you separate out prefill and decode as a separate services, and then you will have to do extra transfer from prefill to decode on KV cache to have decode run with the KV cache. But another thing that's specific to this type of optimization is that you now can do optimization specific to prefill versus decode. So as I mentioned, prefill is more compute bound and decode is more memory bandwidth bound. So you can imagine designing something that has more memory bandwidth for decode servers and for prefill more compute bound, for example. Or you could use different form of corners or different type of utilizations. Or one of the things people are looking into is using different hardwares. Like AMD and NVIDIA GPUs have diverse characteristics, and by using that, you can do a little bit better on the exact settings. And of course, if you have your own accelerators, you could imagine you can have accelerator running, say, decode or prefill, but other ones you just rely on H100 or AMD GPUs. So DISAG requires you to serve in multiple, say, devices. Another form of distributed inference that requires n devices is through parallelism. And the reason why you require parallelism is either you require memory, you don't have enough memory capacity, or you are bounded by performance. So, for example, if you cannot have all the weights on the single device, that means your memory capacity is out of memory. So one way you can mitigate the problem is maybe offload it to CPU and then load it when you actually need it. But that comes at the cost of the latency, because usually the memory has much higher bandwidth than the connection between CPU and GPU. So that means if your latency constraint is okay, then maybe you can still go with one single device using offloading. But in general case, if you are latency bound, if you're bounded by memory capacity, you'd have to parallelize it somehow to get reduce the memory pressure. So here I listed out a bunch of parallelism techniques. I won't go into details, but if you search for these terminologies, you'll see a bunch of papers around how they do it. The one I'm showing is for tensor parallelism, how you do it for self-attention versus the FFN part. And then there's context parallelism, pipeline parallelism, and the expert parallelism is sort of more tied to a mixture of experts. And then data parallelism is something that's rare, that doesn't mean much in the inference perspective, because it's basically different servers serving different requests. But this becomes a little bit more important when you are using expert parallelism, because you're transforming some parallelism between data parallelism and expert parallelism. Again, I won't go into details, but if you look at some of the open papers around mixture of experts and how they serve stuff, then you'll get the idea. So assuming n devices and some practical range of n for number of devices, then this is how you see across different parallelisms. So roughly you usually get memory reduction by 1 over n. But for context parallelism and expert parallelism, because you are only parallelizing, reducing, like you're duplicating some of the weights, but not duplicating some parts of it. So your reduction is going to be less than 1 over n. For latency reduction, in most cases, you'd expect it to go down by n. But it also depends a lot on the conditions. But roughly, you can assume there will be, like compute-wise, you'll reduce by n. There's some communication overhead which reduces it to be lower than 1 over n. And pipeline parallelism, you're not actually reducing latency at all. And whenever you parallelize stuff, you actually have to introduce some communications. And communication overhead, I just roughly said high for tensor parallelism and medium for context parallelism and expert parallelism, and then low for pipeline parallelism. Here, the important part is both message size as well as how frequently you're doing transfers. For example, tensor parallelism is high because you have to do or reduce like twice a layer across all the layers, versus if you're doing pipeline parallelism, say you're cutting into 4 pipelines, then you only have to do transfer 3 times across whole decode iteration. So like message size is also important, but your number of transfers are also as important for determining the communication overhead. So now we'll move on to sort of takeaways. So as we discussed, we have seen that parallelism is sort of requirement, and also DISSEG sort of requires you to do multi-host inference, which means although many startups designing accelerators are talking about like how they do compute, how they have memory and stuff, but it's not just compute, but it's also about memory. And if you look at, for example, cloud TPUs, you'll see that they, I don't exactly remember when, but they started using HBM similar to GPUs because of memory, like bandwidth and capacity requirements. And similarly, you have to have solution for multi-level network. Like, as I said, like cloud TPUs, they have high bandwidth network through optical channels. And like NVIDIA, I'll go through them in next slides, but we'll have multiple tier of networks that has different bandwidths and different domain size that you can support. And I mean, initially I was talking about training on the scale of cloud TPUs, but this is not just for training, but also for inference. So as you can see, you have to think about accelerator itself, but you also memory and multi-level network. So if you look at NVIDIA roadmap, this is basically what I took out from their announcement on Blackwell. So you'll see that dense compute is increasing, and here like Blackwell and Rubin Ultra, like they are projected, it might not come out as is. And same for other parameters as well. But HBM capacity, you are also increasing proportionally. HBM bandwidth is also sort of increasing proportionally. And then there's 2 layers of networks that NVIDIA sort of does. So one is NVLink NVLink. This one is for small domain, like Hopper series can support up to 8 GPUs. Blackwell Ultra, they can go up to 72 GPUs. Rubin Ultra can go up to 144 GPUs. So like similar to cloud TPU, in terms of cloud TPU's perspective, is sort of pod that is similar to this concept, but you are sort of increasing the domain number of GPUs that you can do fast, high bandwidth interconnect. But at the same time, you'll see that NVLink bandwidth is also doubling every generation. And then secondary network is InfiniBand or RoCE backend networks. So what they do is basically every GPUs will be connected to each other, not just through NVLink, but through a secondary network. This one, as you can see, is much lower bandwidth than NVLink bandwidth, but is still higher bandwidth than, say, typical TCP/IP Ethernet network. If you go, so assuming you have to balance out memory and network, now it comes down to ML accelerator. And most of the stuff I'm writing here is more from the HDPU involvement. But typically, hardware development time is 2-3 years. But ML ideas, they come out every few months. Like, for example, if you look at LLM inference, ChatGPT thing became popular in about 2 years ago-ish. And then like between then and now, we have already seen a bunch of things like MOE being state of the art from dense model, speculative decoding or parallel decoding becoming popular, distillation being very popular, what else? Like reasoning becoming very popular, which has more decode than other cases. And of course, that comes with the reinforcement learning. And these kind of things came out within 2-3 years. So if you started developing accelerator, customizing for the use case, say 2 or 3 years ago, then what you get would be very old accelerator, which doesn't support all the use cases. So there is where you have to think about specialization versus generalization. And the bottom diagram is just an illustration of as you specialize more and more, you can extract performance more and more. But as you generalize more and more, like if extreme would be CPU, then your performance wouldn't be as good as what you want it to be. So I mean, to be honest, there's no right solution for how to like what is a good amount of specialization or generalization. But this is sort of the framework you have to think about, like what is the things that you want to be more generic so that you can support those, or versus what are the things that you think is specific enough that you can specialize on. So one example is that training versus inference. I mean, like LLM inference is becoming more similar to training in some sense, but still, like you'll see that in recommendation model as well as LLM, we did a breakdown between requirements for training versus inference. So it is, and training inference division will be sort of stable. We don't expect like training to go away, or we don't expect inference to go away. So that's why Amazon or Google, they would build some customized SKU for training or inference, which makes sense, right? So similarly, if you think some trend is going to be the same, you could start doing something similar as a specialization. One thing is, like, for example, if you are customizing for large language models, as I mentioned, prefill and decode has different characteristics. So you could come up with an idea that maybe I'll shoot for different SKUs for prefill and decode and maximize the performance out of that. So those are kind of ideas where you want to think about what is something trend that won't change in 2-3 years. This is more sort of technical stuff. One thing I have also learned is because timeline is very tight, and to be honest, these days, if you are trying to design an ML accelerator, you are already late into the game. There are too many accelerators that are being good, and you might want to shortcut yourself by like reducing the scope of the work that you have to do. One of the common things I've seen in the past is you sort of have limitation in memory address alignment. So like certain memory operations, you have alignment requirement that it works if you are aligned, but if it doesn't work. But from my experience, that usually bites you in the long run. You should be sort of go in a direction where your performance limited, not functionality limited. So if it's aligned, you get best performance. If it's unaligned, then you get worse performance, but it works. So one example of why this alignment issue didn't work out well is like you would have like usually that means you have to introduce some of the software paddings to work around this alignment issues. And in ML, you have reshapes or concatenations or other operations that might add stuff up together. And in such cases, your padding sort of keeps growing and growing. And usually, if you want to reduce the overhead, you would have to insert some new operations that would get rid of some of the paddings, which is extra overhead, which might be slower than, say, if you had an online version working. And another thing I'm seeing is that you do, because if you control all the hardware runtime compiler together, you want to define feature responsibility well between those different things. So for example, where things could end up is probably depend on how much information is available and how much design complexity or efficiency you can get out of it. Like for example, compile time, there are a lot of runtime information that is not available to you. So some cases you cannot do it in compiler, even though if you want to move it there. Versus there are some runtime stuff that you can do, but it involves CPU hardware communications. But if you do it in hardware, then you don't have to worry about it from the software perspective, but that can increase complexity. So one of the things that we did for HDPU, this is part of the patent, is that when we are doing preemption for this sort of accelerators, we usually use scratchpad memory to sort of make it power efficient and let software do the memory management. But that also comes with the downside of being when you're doing preemption, you have to manage that scratchpad memory. And if hardware is responsible for managing all of that, it could be very expensive. One thing we did was basically have compiler to sort of analyze and like know where things are ending and where lifetime of the certain memory structures, and use that to sort of give hints on which are the efficient context switching points. So this is where if you have all the information about, like if you can leverage both hardware and software, you could do better things without being too expensive. One of the few things that I also encountered with ML Accelerator is that numerics bugs are really hard to debug. Few cases that comes out of my head is like there was some hardware bugs before I've seen in handling negative values. And before we used to use ReLU a lot, which is nonlinear function that zeroes out all the negative values. So what ended up happening is when we actually run a lot of real models with end-to-end testing, you don't see this hardware bug manifesting in a large manner. But then once you switch nonlinear function to different ones, then you start seeing the issues and you have to fix it. Another thing is in TensorFlow, image resize like upsampling and downsampling, they used to have some implementation that was different from OpenCV or like what computer vision people used to do. And interestingly, like ML models, because you train, like even if your resizing is not optimal, ML model will adapt and give good enough performance. But like one thing I observed is if you actually give the right image resize functionality to that, then things like ML model is not trained for that, so it doesn't work well. So you have to retrain it. So like in this case, you actually had a not numerical bug, but some bugs in resizing function, but ML model did it like trained through it, so you don't recognize it until you actually go down and debug it like one by one. And also like ML model is basically floating point numbers here and there, and it's hard to put semantical meaning into intermediate values to sort of say, oh, like this is where you started going wrong. Another thing is, even though mathematically equivalent, if you run it, it might not be numerically equivalent. Like if you change corner implementation or optimize stuff, it depends on data types as well as accumulation data types and accumulation order, as all of you know. And this makes it hard because if you have some new implementation or new optimization that changes numerical results. And if this is within, say, error range of 0.1%, it's hard to tell whether it's bug-free or it actually has a bug, but that didn't come out as significant for this particular model. In HTPU, we had a bit exact testing framework, which sort of knows about hardware details and compiler passes, and it tells you this is the exact order and exact numerics that will be running on hardware, and you just exactly run them through the software and reproduce those numerics. So this is one of the ways you can go with. This is probably not the only solution, but one of the ways you can debug stuff. Other hard bugs were concurrency bugs, especially synchronization or deadlocks or missing synchronizations. These are because, especially if your accelerator does a lot of concurrency, it's hard to reason about like thousands of compute units going together or data reads and all those things going together and whether things will break or not. Like we have seen something like some architectural specification comes in around concurrency, and we like experts review them and we thought it'll work. And then once we actually go down and implement all the use cases, we happen to see cases where you cannot synchronize correctly or deadlock can happen, something like that. So like here, like formal verification sort of seems to work, but very limited because it like formal verification is really hard to get it right, and there's very few people who can actually do it right. But another way you can help is if you can do extensive end-to-end testing beforehand, before you finally conclude stuff, then it usually helps. But again, there's no, say, like good, like perfect solution to this, but it depends on the situations. Another thing I would go for is software is much cheaper. Software development is much cheaper than hardware or even like doing model experiments. And usually like exploring as much as possible, generalizing as much as possible, abstracting out as much as possible is good in the longer term, even though it might create more work for you now. And also people don't say it much, but having tools or frameworks or flows that are automatic really helps you when you're trying to iterate fast. One example I have is basically, again, for HTPU, we basically had all the new features that are going into the next generation hardware in software simulator, and the compiler actually compiling it for all the imagined use cases. And we were like exercising them thoroughly even before tape out. And that helped a lot because you actually find a lot of bugs even before touching hardware, but across simulator and compiler. And this is like, basically this is much cheaper than sort of waiting for RTL to be available and testing out on there. One model co-design is one thing people don't usually think that much as an infrastructure person. But one thing I would add is like you shouldn't consider ML model as a fixed. Usually biggest gains come from changing model architecture. And one example here is depth-wise separable convolution. So depth-wise separable convolution is something in old times they used it for mobile CPUs where you reduce computation a lot, but conceptually having similar concept as a single large convolution. But this actually depends a lot on hardware. Like for example, in this blog, I had a link here. Basically, HTPU, we like depth-wise convolution was not supported well in first generation. So actually using the fused convolution was performantly better than using depth-wise separable convolution. So here, if you are saying, oh, like everyone in the mobile land uses depth-wise separable convolution, so we should if we go with the path saying, oh, we should support that well, then we might not have seen this gain. Another thing is mixture of experts or any sparse type of stuff where you see a lot of improvements without like sacrificing performance that much. And obviously quantization, pruning, those are also trading off quality with efficiency in many cases. So those are some of the takeaways I have now. Some of the interesting directions I foresee from large language model inference is some of are listed here. So I think it's like, at least for large language models, it seems like distillation seems to work surprisingly well. And what this means is now you don't have to train for inference efficiency, but you can train in a way that will get best quality, and then distill down to some inference model architecture that can run more efficiently for inference. I mean, there are still more questions and things that we have to resolve going in that direction, but I think this is very encouraging results and interesting directions that people should get into. And then inference use cases, there are diverse inference use cases coming up. So there's online serving where you have some tight latency constraint and you want to maximize throughput. There's offline serving. This is for generating a lot of data or checking evaluation scores and so on. Here, like, you more care about maximizing the throughput. Latency constraint is not as high because you just run batch stuff and then you get the results. Reinforcement learning is somewhere in the middle. So you don't have as strict latency constraint as online serving, but you do have some latency constraint because it usually comes with something like you do inference and then you do training and then you do inference and training. I mean, at high level. So there, like how you optimize software stack or hardware might be a little bit different for our use cases. And then there's, again, capabilities like long context. People are talking about long context a lot. Here, based on the current costs, it seems like sparse attention is sort of a requirement. But as I said in the beginning, I don't think there's a consensus on what is the good way to do sparse attention across the industry. Maybe each team, like each company, has figured out something in different ways and just go in that direction. But I don't think there's a common consensus around that. Reasoning is more about decoding, and here speculative decoding or parallel decoding will help a lot in terms of performance. And there, I think it working out well is a good thing, but why it works out that well, and is there something we can do better than that, is something I think is still open questions. And then there's multimodal and a few other like speech or whatever capabilities, taking it different inputs from text. I mean, it has been out there for a while, but I think compared to text-only cases, there's not much studies around like what needs to be done here or what could be done differently and so on. So that's the end of my talk. I'll be happy to take any questions, and I'm also happy to get emails if needed. And also a little bit of a plug-in. My team is hiring aggressively. So if you're graduating or even if you're looking for internship next year, please email me or apply. We are open to all the applications. Thank you.
Well, thank you. Thank you for the great survey of the current state of, the, I guess about, I don't know what I should call it, the, LLM, inference, more or less service.
Mm.
So please ask questions. Okay. Can you turn on your mic and then speak up. There's a one